Okay, so this work I did together with Alejandro Russo, who's a PhD student in our department, and John Hughes. And okay, better. Okay, so here's a little motivating example. The way you deal with passwords on Unix systems. So it used to be the case that there was a file called etc/password where you would store a file with one line per user, and it would have all the information about the user, what shell they use, what their name is, and also an encrypted version of their password. And this file had to be accessible by everybody. And that's of course not so nice, because then if somebody breaks into your system, they can read this file, and then they can do an offline a dictionary attack or something on the passwords, and then they can get your passwords. So on more modern Unix systems, there's a slight variation of this, where this file, the password file, is broken up into two files. One is shell and the other one is password. And unlike what the name suggests, the password file still contains all the information except for the passwords. And then the shadow file actually contains the passwords. And everybody can access that file, because if you want to know what a user is called, or what shell they use, or whatever, you can go to that file, so that's fine. That's not secure information. But the information in this file should only be accessible by people we trust. Okay, and so that feels much more secure. But then, when you actually read the Linux manual that says how to deal with this shadow password file, it says, oh, it's actually quite simple to add shadow support to a program. The only problem is that the program must be run by root in order for the program to be able to access the shadow file. In other words, if any program wants to do anything with root, with the shadow file, then the program has to be root, and then the program can do anything, which is not so nice. So what we would like to do is to write programs where we have more control over what information flows where, and who has access to that information. So, more general version of the problem is that suppose somebody intrudes in our system, they will get some kind of rights of the user that they cracked. We don't want them to have access to everything. Or even people that we invite to our system. For example, when we run somebody else's plugin, we would not like this person to start reading our mail or something like that. Or even for ourselves, if we're writing programs that we don't really trust ourselves, it's very easy to make mistakes when you're programming. We don't want to suddenly write a program that we allow others to access, and then those persons that maybe abuse our program to get to our secrets. So these kind of people we don't trust. And so we want to have a programming language where we're able to restrict access to data, where does data go, and where it is used. And this is an area called information flow security. So what is information flow? Well, I'm using the following model. We already saw this at SAP. People talked about this, but a program is a model that is taking a bunch of inputs and producing a bunch of outputs. And then we classify some of the inputs as high security and some of the inputs as low security. So people we don't trust, they can see the low information, but people we don't trust cannot see the high information. So only the trusted people can see the high information. The program does some computation and spits out some high information and some low information. And if we look at the allowed information flow that this program can have, then of course information can go from low to low, and information can go from high to high. And even information can flow from low to high. So the low, we have the user presses a button, everybody can see that, but it could actually influence the high data, that's fine. But the information flow that we want to restrict is we can't have information flow from high to low. So that's the sort of the definition of information flow security. And a little bit more formal is this property is called the non-interference property, meaning that if you have a function like this and you vary the high inputs, then the low outputs, if you vary the high inputs, the low outputs should not be affected. It says inputs there, I should say. Okay, as I said, I'm going to talk about the attacker. And the attacker is anybody that we don't trust. It might be an intruder, it might be some other programmer, or it might be yourself. So we also want to protect ourselves against these kind of things, just like we use a type system to protect ourselves from making certain kinds of mistakes. And we assume that everybody, including the attacker, can observe low security outputs. But only trusted people can observe the high security outputs. So this has been a study for about 30 years. It's a very active research field, lots of conferences. And the field has produced, so there's lots of theoretical results about these things. The field has produced a number of compilers for languages that have this information flow built in. So there's a compiler called GIF for an extended version of Java that was made in 2001, and there's one for a language, an extension of ML called FlowCamel at Inria, but it's not actively developed anymore. And unfortunately, the impact on practice of these compilers is limited. And so the reason, I think, is that in order to use these languages, you have to learn a new language. It's not Java anymore, it's not OCaml anymore, it's another language. And so maybe certain libraries are not supported anymore, and these kind of things, and you have to learn a new language, and it's a big impact. Also, so I think the theoretical underpinnings of GIF are not so good, so every now and then people find mistakes in GIF, so it's easy to write unsound programs in GIF. So, of course, if you're a Haskell programmer, then you think, well, why would we make a new language? We just make an embedded language. We make a library for information flow, and this has also been done by people. For example, Steve Stanselic and Lee made a library in 2006. That was a Haskell library, and they used arrows for this to control information flow. Yeah, if you think about it, arrows are very nice. They are all about information flow and data flow, and so arrows fit quite nicely with this information flow idea. And the advantage of doing it like this, you don't need to write a compiler from scratch, you don't need to design a new language from scratch, so you can quickly experiment with new ideas, etc. Okay, but there were some limitations to their approach. So for example, they didn't deal with side effects like file I/O and these kind of things. Actually, there was an extension made at Chalmers by Master and also Alessandro and John were involved in this. And they made major changes in the implementation of the library, and they came up with new arrow combinators that didn't follow the actual arrow standard definition, so they couldn't use the arrow notation. But they solved some of the problems, and the focus was a little bit different. So that was, of course, a disadvantage. So already using arrows is a disadvantage, I think, because the syntax is a bit more clunky, people are not so used to writing arrows, you're more restricted in what you can write. And then, of course, especially if you go out of the arrow notation, you should motivate why do we use arrows. And actually, in the original paper, they claim that monads are not suitable for doing this. But there's no proof or something, it's just mentioned on the fly. And so this paper is all about exploring what happens when you actually just use monads for this. So our approach is a lightweight approach. It's library-based. It's monad-based, so arrows are not anywhere inside. We restrict capabilities of functions by using abstract types. So we make use of the module system that certain modules cannot do. I think that happen in other modules. And we believe it's practical. Although there's a question mark there, the library was developed over the last half year or so, and we've done some examples, but of course we don't really know how practical it will be. So why did we pick Haskell? Well, for this audience, maybe I don't have to motivate, but Haskell has some kind of nice features, such as it's a pure language, there are no side effects. And that means that we have control over the side effects. So side effects are a big pain in all the other languages that deal with information flow, because there's something that is called implicit information flow. So here's a little program. If you have a secret variable that contains a secret, you can branch on the secret, you can check if it's 3 and then you print 1, otherwise you print 2. And then they say there's implicit information flow here because the value of secret can affect the output. So and secret is not used directly in the computation of the output, but it's used indirectly in the control of the program. And if you're in a pure language, implicit information flow doesn't exist because everything is just function application. Even if you have if then else in Haskell, that's still just a function application. Okay, and also the strong type system of Haskell is nice. You cannot cheat, so there's no way to go around unless you use functions that start with the word unsafe. So here's a little example. Suppose we have a function f that takes in a pair of an int and a character and produces a pair of an int and a character, but just assume that the int is secret data and the character is not secret data. So there are a number of examples. We'll just quickly go through these. So the first one, a secure function. It takes the n and the c and then adds 1 to the n and adds 1 to the c. Well, that's fine. There's no information flow from n to c. And the second one is fine. Also, we use the value of c to add to n. That's also fine. But this one is not fine. Why not? Because we directly use the value of n to create a character on the low output, so that's not good. And here, this is also not fine because we branch on n, and so all that data will be dependent on n. So that's also not good. So we want to catch these with the help of the type system. So here's a very simple security API that our library is based on. So our library is a little bit more general than that, but let's start here. So suppose we have an abstract type called sec array, and we have two functions that work on this type that you can see. So there's a function called sec, which takes a value and inserts it in this type, and there's a function called open, which takes a sec array and a key and then gives you back the A. Now you can see if you don't have the key, you can't get the A. So if I give you the sec array, you can do whatever you want with it. But if you don't have the key, you won't be able to open up the secret and you will get the value. Okay. So what is the key? Well, the key is just a data type. Data key equals the key, and this is a hidden data type. So we use a module system. All the modules that can see this constructor function, they can open up the secrets. All the modules cannot see it, they cannot open up the secret. And of course, open needs to be a strict function. Otherwise, you can just put on the find there and you're cheating again. So open needs to be strict in the key. And to make this abstract type a little bit more useful, we can say it's a functor in a moment, so we can actually compute with the values that are in the secret, although we cannot look at them. And that's very nice. So since it's a pure language, you can go inside, but you can't leak any of the secrets. So we all know how frustrating it can be sometimes when you are in the IO monad, you can't get out of the IO monad. Well, the same thing here. If you're in the sec monad, you cannot get out of it unless you have a key. And only trusted people have a key. So that's good. So what this gives you is a way of limiting access to the values, but you can still, anybody can still compute with them. Okay, so the example I just gave you, a little bit more general, but now the function f will have the following type. F takes a pair of sec of A and B, and produces a pair of sec of C and D for some types A, B, and C, and D. And that means that the low security output D cannot depend on the high security input A, because otherwise it would have a sec around it. And so we have this non-interference property. If we know that f applied to some secure value A1 and some low value B equals to C and D, then we know that if we apply f to another secure value A2 and the same low value B, we get the same low output D, and that maybe possibly is different secure output C. Okay, so that was very simple. The actual library is a little bit more general than that, because knowing the key or not, that gives you only one way of having given restricted access. In practice, you would like to have several different security areas or different levels of security that you want to give to different parts of your program. And the library allows that by just generalizing a little bit. So we have an extra argument to the set type, which says what the security area is, and that's given by a new type. So instead of having a key, we just have the s there as an argument. And then we can build any kind of security lattice or any kind of security structure by just making a number of different types for each security area that we want to have. So H stands for the high security, and it has a constructor H, and that's an abstract constructor. Nobody can see that unless they are trusted. We have a low security area. Actually, we don't really need the low security area because everybody can see the L constructor, so everybody can open up those secrets. But it's nice to have them there anyway because you can write generic functions over secrets, and even the lowest level programmers, they can still use those functions. And these guys, so we can make any number of these types, and they are connected with a type class called less, which implements security lattice. So that says that's interesting to have. So if you have security access to a particular area, then you have access to any area that's related to it. So for example, if I have two areas, low and high, then if I have a secret in the low area, I can turn it into a secret in the high area. Okay, so that allows you to sort of bunch together number of security levels without having to explicitly program them up, all of them. And there are some instances here. Okay, and as I said before, set of L of A, that's just the same type as A, because you can open it up and close it up and everybody has access to the L. So what does your program look like if you use this library? Well, your program is a big green blob, and it consists of a number of components. So over here in the yellow part, we have all the Haskell libraries. And we have decided that some of the Haskell libraries are safe, namely all the ones that have pure functions, those are safe. But some of the IO modules are not safe because we can do strange things with them, and especially the ones that export these unsafe functions, those are not safe. So a subset of these libraries are safe, and only those libraries you can use in this green part of the code. And this green part of the code is written by the attacker. So anybody can do anything here. If you have a jet lag or you have a hangover or whatever, you can write this code. That doesn't matter. As long as you don't write that code when you're sleeping, when you write the red code, because that's the trusted code. That's the code that we write. And that code gives decides what kind of access they get. Okay? That code can use any Haskell library it wants because we trust it. And then what we provide in this paper here, we have these two parts to our library, the blue things. We have a library called seclit.hs, and there's a public version of it, and there's a trusted version of it. And the attacker can use the public version, so that gives all the sec things and the open and the key and all that kind of stuff. And the trusted version gives all the access to the internals of this library, so the trusted code can exactly say, you get this capability, you get this capability. And of course, in general, you can have many of these green parts that are written by different people, and the trusted code manages the information flow between them. Okay, so yeah, so in that part is all I/O, unsafe performing FFI and all that kind of stuff. And part of that we give back in the safe Haskell libraries that we implement. So our library gives you a to I/O, but you can't use I/O directly in those libraries. And it's about 400 lines of code, the total thing. So that's the lightweight thing. Okay, so how about I/O? There are sorts of I/O features that you would like to support: file I/O, send in, send it out, state references, channels, and these kind of things. I will only show file I/O in this talk, and in the paper we only talk about file I/O, but we did actually state references and send it in, send it out as well. The channels we haven't done, but I don't see any difference between the way we solved that problem. So the file I/O problem is solved in a particular way, and I think this is what you can use for all of this. But it's a lot of work to implement all of that, so we didn't do that. So here's the first try that you might think. You might think, okay, we have the sec thing, so why do we need something more? And here's a very nice I/O library that doesn't make use of anything extra. So we introduce a type of a file, which is an abstract type, and it is annotated with S. And that means that the secrets in that, or the information in that file belongs to the secret area S. Okay? So that means that you can write the secret file S, in the normal I/O monad, and you get back the secret string. So you don't get the string, you get the secret string, and only if you have access to that security area, you can actually look at the file. So that's nice. And similarly, write file set. If you have a file and you have a secret on the right level, you can write that secret into the file. And of course, if you have a secret on the lower level, you can always wrap it up in a secret and write it to the file also. But you can't leak any secrets by writing high secret strings to low security files and then reading them. So that's the thing that we want to avoid. So these two functions, they work very nicely. There's nothing wrong with them. You can actually use them in your program. But they're not enough. This took me a while to realize. I thought, okay, we did the sec thing, that's done, okay, we have a very nice paper, let's write it. And then our combo came and said, well, are you really sure? There are some things you can't do. So suppose we have a program that does something like this, depending on some kind of high value, we either write file 1 or to file 2. So that means that we have to look at the value, and then we get an I/O action that depends on what the value of that value is. So then you can the simplest I/O actions have this kind of type, but we might have types where we have secret, and then what side effects we do belongs on secret, so that's in the I/O, and then the result is in the secret again. And then if you generalize this, you get all these kind of types that are nested like that, and that is not really practical to do. And in fact, you can't really work with this at all. So we need a new type of secure I/O. And some people say, well, why don't you just provide a collapsing function that collapses some of these things and then you repeatedly apply, but that becomes unsigned. That's a challenge to you. Come up with a collapsing function that doesn't leak any secrets. Okay, so there is a simplified version of the library that we provide. So we have a new monad, IO monad, which is called sec.io, and it's parameterized by an S. And what does the S mean? It means that if we are computation in this monad, they can read from that level S or lower. So they can read secret at the level or from lower. They can write to the secrets to that level or higher, and the value that they produce, the A, will be a secret at the level S. Okay? So then here are three simple functions that we provide, and in general the library is a bit more general than this, but if we have a secret at level S, we can peek at it in the IO monad, so that's just a lifting function. And we have files, we can read them and so if we have a secret file, we can, at the right level S, we can read the file, we get like a string in our monad, not a secret string, but a real string. And when we write it to a file, we just write any string in the monad because that has the right security level. And finally, when we have a secure computation on the level, we can run it, get back an IO computation, and the secret, the final result is wrapped up in a secret. Okay. And what does this mean? This means that the side effects you do escape the secret. So this is the reason why you can't implement this only using C. You have to break the abstraction of C. So the argument from can do, depending on secrets, can decide to write or read from different files. And those actions are leaked. But we assume that those actions are not observable within your Haskell program. So whether or not you write or read from different files is not observable from your program. And those are the only things that are leaked. The actual results of the computation are not leaked because they are wrapped up in the secret. Okay, and the library is much more general than the paper, but I don't have time to go into that. Okay, so here's an example that says, depending on the secret, we do different things. We can peek at the secret, and then if it's 42, we write to file 1, and otherwise we write to file 2, and that works fine. This matches. Okay, so here is how we can do the shadow and the thing. So we have the untrusted code, which the attacker writes, and this has a main function that takes as arguments all the capabilities that the trusted code gives it. So we give it a high security file, which is the shadow file, and a low security file, which is the password file, and then it can do anything kind of thing there. And then how does this main function get all these arguments? Well, the trusted code creates a high security file shadow, a low security file password, and then runs the main function of this one. Okay. So I'll skip this. Okay, so one more thing I want to say that our library provides that none of the other libraries provide, which is really nice, is in practice, information flow is way too restrictive. When you try to write real programs in it, it doesn't really work. For example, already, if I have a password that is secret data, and the user types in their password, and I want to check that their password is the same, what I do, I encrypt this one and I check if they are the same. But I can't because this is high security data, and telling the user if that password was correct or not, that's low security data. So there will be information flow from high security to low security. So that's not good. That doesn't really follow the non-interference property. So this is solved by something called declassification, which is a quite new thing in the security area. And the idea is that if we look at the model that we had before, we allow all this information flow, but a little bit of information can flow from high to low. And exactly how little that is determined by the trusted code. So the trusted code can give capabilities to the untrusted code to leak some of the secrets, but only in a very limited way. And the paper provides combinations for doing that, but I don't have time to go into that, so let's skip through that. Okay, so correctness of this. So that's a very good question that Ralph asked in the last talk, and for this talk I have some answers. So for just the sec part, I think it's almost obvious and trivial that this is correct, although maybe Ralph will start complaining. So
I will.
The proof of this is in the technical report, and it uses operational semantics, and it follows the standard way that the security people prove non-interference for these kind of type systems. But that's only the sec part of the library. All the other things, sec.io and files and these kind of things, we haven't done yet, but that's future work. And my original goal was to just make a very, very small library that you could trust, like the sec library, that would, to me, be obvious and trivial, and then build everything on top of that. But as I showed you, the sec in combination with AO, it wasn't really enough to have that. So I've been looking for many months for a slight extension to the sec library that allows me to implement sec AO, and so I only have to put records with that slight extension, but I didn't manage to do that. So that's also future work, and perhaps it will never be done because I have no idea how to do it. It says stop there. Okay, so here are my conclusions, and I already said everything, so let's get questions.
Thank you very much, Koen. Any questions?
Just so you have a portion of the Haskell library that you designated as safe, and you're not going to use stuff like stuff that you designated as unsafe. Does the unsafe portion also include functions you write yourself using the safe portion and maybe some pattern matching?
Sorry, say that again. The unsafe part.
Is pattern matching safe?
Yes.
Okay, including complete pattern matches that you might map over your secret under.
Yes.
Okay.
In the order, exceptions are not part of the thing. So the program can crash in a secure thing, but it can never be observed by the trusted code that it's actually crashing.
You won't be able to catch it from outside that.
You can catch it in the trusted code, but that's the trusted code, so they can do whatever they want. So the untrusted code cannot catch the exception. So you can crash. You can go to a secret, say if it equals 42, I say crash, but then you can't see that, so you can't do anything about it.
Any other questions?
In your model, you provide confidentiality of secrets. Would a similar model be capable of providing authenticity or integrity?
So I think yes, but we haven't done it, but we have discussed it. And we decided to only stick to confidentiality. So, for example, if you have access to a high security file, you can just write garbage in it. And that wouldn't be good. But you can turn it around and also limit the accessibility of writing to rather than using information. But we haven't done that. But it works quite similar.
One last question, Jack.
Can you put the anatomy diagram back on, please? I have a rather naive question about it.
If I knew how to...
Maybe I can do it without. So down the left-hand side,
I can describe the picture well.
down the left-hand side, you have two blue boxes.
Yes,
With the trusted stuff and the non-trusted stuff.
that's right.
And it all depends on the attacker having only the non-trusted version.
That's right.
So,
Or, yes.
how's that enforced?
Well, currently not. I mean, so the GDC doesn't really, you can't really say in GDC, check that this module only imports these. So that's something that you have to write your own tool for that says, oh, this module only imports these modules. So that's sort of outside of this code.
Thank you very much, Koen.